Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be exploring the process of solving single variable linear equations. We're going to start by really kind of defining what a linear equation is in the single variable sense, and we're going to look at the different properties that we can use to help us actually go ahead and solve these equations for a given variable. Now first we should define what a linear equation in a single variable is. We're going to be working with linear equations in the future quite a bit, but we're going to work with them in multivariables. But let's start by defining what a single variable linear equation would be. We need to first start by saying that a, b, and c are real numbers. So this means that we are going to use a, b, and c to just represent numbers. We should remind ourselves that real numbers are going to be defined as any number on the number line. So a real number right now is any number you can probably think of. Any number on the number line is a real number. So you might say something like 1 or 2 or 7 or 1,673, or let's pick a negative number, -4. What about a fraction like 5/7? What about something like pi? Pi is a real number because that's on the number line. What about a number like the square root of 2? What about something like 3 pi times the square root of 7. I don't know, something complicated like that. The point is, all of these numbers are real numbers, okay? Real numbers are whole numbers, they're positives, they're negatives. 0 is a real number as well. I guess I should include that. The fractions are real numbers. Irrationals are numbers as well. Irrationals are things that can't be written as fractions, things that have decimals that go on forever and ever and never repeat a pattern, like pi is an irrational number, square root of 2. So really, any number on the number line is a real number. That's going to be our working definition for real numbers. There are much more formal definitions to this, but this is what we're going to work with. And the symbol that we're going to use for real numbers is a bold script R. A bold R, now we can't write in bold. I mean, okay, maybe we could do little box lettering if you're pretty artistic. But in the textbooks, you'll often see real numbers written with a bold capital R. To do that in handwriting, we often use these kind of double lines when making the R. So it's got a kind of double line to it. So that symbol means the set of real numbers, the collection of all the real numbers, okay? So pick 3 real numbers. Any 3 real numbers you want, and let those be A, B, and C. So they can be anything. We're not going to name them because they can be any number you want, but just in your head. And also, make sure that A is not equal to 0. So don't pick 0 to be A, okay? That's going to be kind of a trivial, not important case. So just pick any other number. B and C could be 0 if you wanted, okay? But just make sure A isn't 0. So we're going to define a linear equation in one variable as an equation that can be written in the form ax plus b equals c. What we mean here is that a linear equation needs to be able to be written as some number times the variable x plus some other number equals a number. Okay, that's kind of weird to say. So let's try to make some examples. Let's actually put some examples together of what a linear equation in a single variable might look like. So I'm going to clear some space here and let's take some time to actually write out some examples. So I'm going to pick 3 numbers. I don't know, let's pick 2, +3, and 7. There, 2x plus 3 equals 7. This is a linear equation in a single variable. And we call it single variable because x here is our only variable. That's our only unknown. And so we have it pretty simply written out. A number times x plus some other number equals a number. Let's pick some other numbers. Maybe let's pick something like 8x minus 5 equals 4. Am I allowed to have a minus 5 here? Because in the form, it says I need to have plus a number, not minus a number. Well, hopefully you're saying to yourself, wait a minute. This whole 8x minus 5 is the same thing as 8x plus negative 5. And negative 5 is a real number. So yeah, this is also a linear equation. Maybe let's take some fractions here. 1/3 times x plus 5/8 equals pi. I don't know. Let's just go with that. This is a linear equation in a single variable because all three of these are real numbers. So we're good there. What about, oh gosh, let's try negative 4x plus 0 equals 10. Is this a linear equation in a single variable? What do you think? Well, hopefully you're saying, yes, it is, because all three of these are real numbers. The only condition was A couldn't be 0. I never said B couldn't be 0, so this is allowed. The only time that wouldn't be allowed in this case would be if I had 0x plus 7 equals 5. This wouldn't be allowed. And you might say, well, why is that? What I'd like you to do, pause the video for a minute, just take 60 seconds and think to yourself, why wouldn't this be allowed? Why can't I have 0x in here? Well, hopefully you were able to see the obvious situation. If I took 0x plus 7, what's 0 times anything? That's just 0, isn't it? And I'm left with 7 equals 5. Is that true? Does that work? No, of course not. That's a problem. So you would say, oh, well, if I plug 0 in for A, if I had 0x, then I might get something that doesn't really work out. Or you might get a weird situation like this. 0x plus 2 equals 2. Again, this just cancels out and you have 2 equals 2. This is kind of a weird situation. We call this a trivial case. And we're going to learn in a little bit what actually these two examples are saying. And really, they don't do much for us in terms of an equation. So that's why we're saying don't pick 0 for A. Pick anything else. Now that we have a linear equation and a single variable defined, I want us to go ahead and define a couple properties that we can use when working with these types of equations. We have what are called the properties of equality. There are two properties we should remember: the additive property of equality and the multiplicative property of equality. And what these do is they help us to manipulate an equation. The first one, the additive property of equality, says if A equals B, then let's say you added C to both A and B. Would both sides of the equation stay equal? If you had an already given equation, if you had two things equal to each other, can you add the same thing to both sides? Can you add whatever C is to both sides? Is that allowed? Will you stay equal? I like to think of this kind of like a balanced scale. So imagine you have a little scale here. So I'm going to draw one of those old-fashioned weighted scales. I'm sure you're fascinated with my artistic abilities. But let's go ahead and let's say we had the scale and it was balanced. One side equaled the other side. So let's say I put a 5-pound weight on this side and a 5-pound weight on this side, right? That's the only way that a scale would be balanced. You had to have the same amount of weight on both sides. But let's say I went ahead and I threw on an additional 3-pound weight to each side. would the scale still stay balanced? Well, hopefully you're saying to yourself, well, of course it would stay balanced. You have 8 pounds on one side, 8 pounds on the other side. Unless the scale was broken somehow, or unless one of the weights was mislabeled, you got the same amount of weight on both sides. It's going to stay balanced. Let's think of this now in terms of the symbols A, B, and C. Think to yourself, okay, A here is just some number, and B is some number, okay? I don't know what they are, just there's some numbers, there's some quantities, okay? And I'm telling you that they're equal, so they're balanced, okay? You have the same quantity on one side that you do on the other side, because that's what it means to be balanced, right? That's what it means to be equal, same quantity on both sides. Let's say I add the same quantity to both sides again. So they originally were equal, and then I take some number C. Again, C is just some number, and I add the same thing to both sides. Will they stay equal? Hopefully you're saying yes, they should stay equal. Because if they were equal to begin with, and you added the same amount to both sides, that's not going to change anything. So yes, if you add the same thing to both sides of an equation, it will stay equal. Hopefully that's something we remember from previous classes and previous pre-algebra work that we've done. But this is a little visual representation of what's going on. It's helpful to remember that when something is equal, it means you have the same quantity. You have a balanced scale. And when you start to manipulate the equation, you want to make sure that your scale stays balanced. You want to make sure that whatever happens to one side, it happens to the other side as well, so you stay balanced. Now, this was called the additive property of equality, obviously because you're adding the same thing to both sides. What if we had an equation, again, A equals B, you're given that these two things are the same, and what if I were to this time subtract the value C from both sides? Would it stay equal? Could I have, let's say, removed a certain amount of weight from both sides? And would it have stayed balanced? Imagine you're holding, you're holding in each hand 10 pounds, right? And someone came and removed 2 pounds from each of your hands. Would the weight still be the same in both hands? Say you're balancing a scale and you started with 20 pounds and someone came and took 5 pounds from each side. Would the scale still stay balanced? Well, yeah, it would. We call this the additive property as well. The reason for that, I think I kind of talked about it a minute ago, but when you're subtracting, that's the same thing as adding a negative. Okay, so this whole idea about subtraction being different than addition, it's not. Subtraction is the same thing as addition. You're just adding the negative. So I'm grouping these two properties together. In your book, they call one the additive and one the subtractive property. They're the same thing. Now let's talk about multiplication. If you are working with an equation, A equals B, you know two things are equal to each other, then what would happen if you multiply both sides of the equation by the same number? Would it stay equal? So again, if we're thinking about this in terms of a balanced scale, let's say we had 5 pounds on each side of the scale, and let's say this time I multiply both sides by 2. What that would be like in this case, meaning I'm doubling the weights, okay? The weights were equal to each other. Now I went and I've doubled them. So now I have 10 pounds on each side. Would they stay equal? Well, of course they would. You're just taking the same weight on both sides and you're doubling it or tripling it or doing whatever multiple, okay? So what the multiplicative property says is, if you're given an equation, two things equal to each other, you can multiply both sides by the same value and they will stay equal, okay? You are not ruining the equality here, okay? Both sides are staying equal. It's not like suddenly one side becomes bigger than the other side. They're staying equal. Now, just like we did with subtraction, subtraction is the inverse of addition. Let's look at the inverse of multiplication, and that's division. If we had two things equal to each other, if we had this equation, then could we divide both sides by the same number and still be equal? Would that work? You can think of dividing the weights as being like cutting the weights in half or a third, right? You're reducing them down. Would these still be equal? Well, hopefully you're noticing the pattern that yes, they would still be equal. The reason for this, again, is because division is just multiplication. Division is just multiplying by the inverse. So a divided by c is the same thing as a over 1 times 1 over c. So there, I just took a problem that was addition and I rewrote it as something that's multiplication. So this is why this works. What I want you to remember from this is that you can add whatever you want to both sides of an equation. You can subtract whatever you want to both sides of the equation. You can multiply whatever you want to both sides of the equation. And you can divide whatever you want to both sides of an equation. And when you do that, whether you add, subtract, multiply, or divide, both sides will still remain equal. That's the thing about solving a linear equation, or really solving any equation. You want the sides to stay equal. You don't want to throw the scale off. You don't want to suddenly change things around and make one side bigger than the other, or vice versa, okay? Now, I said before that you can add, subtract, multiply, divide whatever you want to both sides and will stay equal. There's one condition I need to put on that, and it should be obvious. It comes in the division problem. So I'm going to write this in red so we can definitely see it. You can divide whatever you want to both sides of an equation, it would stay equal, except one number, 0. You can't have c be 0. If you pick 0, then you're saying a number divided by 0. Are we allowed to divide by 0? No, we can't. So that's why we can't pick 0 for when we're doing division. But otherwise, you can pick any number you want. Pick any other real number. Pick whole numbers. Pick negative numbers. Pick fractions, decimals. Pick something like pi, whatever. It will always work. So let's go ahead and let's actually try practicing solving a couple equations. These are some fairly simple ones, but I think it's important before we begin to remind ourselves what is the goal when solving an equation. It might seem rather simple right now, but as we progress in our study of algebra and we learn more and more complex techniques, I think it's helpful for us to really remember what was the ultimate goal of solving an equation. Now, our goal is to isolate x, the variable. We want to get it by itself. That's our goal right now. Now, that's pretty much what we've been doing in our studies of pre-algebra, and this is what we're going to try to identify. What is that missing number? We know that 2 is the same thing as 3 times that number minus 7. Well, what could it be? Use the additive and multiplicative properties of equality to manipulate your equation to get x by itself. That's how we solve every type of equation. You just use the properties we just went over to manipulate this to get x by itself on one side. So, pause the video, take a couple minutes, and let's see if you can get through these 3 problems. All right, well, hopefully you were able to work through these problems. I'm going to go through them rather quickly. The first thing that we want to do in the first example is recognize that we need to get x by itself. Part of the issue is that we have a 7 on this side and a 3. I want just one x by itself. So the first thing I'm going to do is I'm going to get the 7 over. I can use the additive property of equality to move the 7 to the other side. I end up with 9 equaling 3x. Notice what happened here. When I added 7 to both sides, it canceled out on this side. This is called making a zero pair. My goal was, if I added 7 to both sides, it would disappear from this side, and now I'm one less number away from figuring out what x is. Now, 3 times a number equals 9. I don't want to know what 3 times a number equals. I want to know what just one of these numbers is. So I want to get that coefficient, that 3, I want it to be a 1. So what could I do to get a single x here? I don't want 3x, I want just 1x. Well, I'm going to use the multiplicative property. I'm going to actually divide both sides by the value 3. What happens when I divide both sides by 3? Well, 3 divided by 3 is just 1x. And 9 divided by 3 is a 3. So what I just did here was I used the additive and the multiplicative properties to get x by itself. I moved the terms that didn't involve x to one side, and then I used the multiplicative property to get rid of that coefficient. I turned it into a 1. 3 divided by 3 is 1. There's a little imaginary 1 there. So now I know what x is. A single x represents the number 3. So let's go ahead and let's practice that on the next problem here. Notice that I have x's on both sides, and I have what we call constants, numbers that stand alone, on both sides as well. What I'm going to do here, again, the first thing I should try is get all x's on one side. So basically get everything to do with x on one side. So I want to try to move this 4x over to the 10x. But how do I do that? What could I add or subtract to both sides that would get rid of one of these x groups and move it over here? Well, let's go ahead and I'm going to subtract 4x from both sides. 10x minus 4x is 6x, and 4x minus 4x, well, that just cancels out. I'm doing what's called the inverse method. And I'm trying to, like I said before, trying to make zero pairs. I want these things to cancel out. So if I'm going to move 4x to the other side, I want it to cancel out on this side. So what could I add to 4x to make it equal 0? Well, I just subtracted 4x from both sides. And then let's do the same thing here with -3 and -2. I don't want these two numbers, one on each side. I want them to combine together. Well, since I have the x's on the left side, maybe I'll try to get the numbers on the other side. What could I add to both sides to get rid of the -3? Well, let's add 3 to both sides. 3 and -2 is a +1. Take a look at what we just did here. We took something that had x's on two sides and numbers on two sides, and we got it down to where x is on one side and the constant numbers on the other side. All right, so I know that 6 times x is equal to 1, but what's just one regular x? 6 of them make 1, but what does just one regular x do? Well, to figure that out, I'm going to again divide both sides by 6. What happens here is when I divide by 6, I get 1x is equal to 1/6. I know what one singular x is equal to now. Again, what did I do? I got all the x's on one side, everything that didn't involve an x to the other side. Then, I guess I could say step 2 was get the coefficient. Remember, the coefficient is the number in front of x. Get the coefficient to be a 1. Okay, because that's what we're trying to figure out. What does one single variable represent? All right, let's take a look at problem number 3. Again, I have a 5 on one side, a 3 on the other, and the x isn't by itself. So one of the things I want to do is get rid of that 3. Let's move it to the other side. So to get rid of it, I'm going to subtract 3 from both sides. I'm allowed to do that. That would mean that these cancel out, and I'm left with a 2 equals x over 4. All right, I know x, some number divided by 4 gets me 2. Well, what does a regular x get me? Not one that's been divided by 4, but just a plain regular x. Well, to make that coefficient a 1, I'm going to multiply both sides by 4, or 4 over 1. I'm allowed to do that. I can multiply whatever I want to both sides. What happens here? Well, the left-hand side becomes an 8. Let me move my work over here. So that becomes an 8, and the right-hand side becomes 4x over 4. Well, wait a minute. What's 4 divided by 4? Oh, that's just a 1. So I have 1x is equal to 8. These are some fundamental, rather simple problems, but we're making sure we're using the additive and multiplicative properties of equality, okay? All we're doing is we're adding whatever we want to both sides, and we're multiplying whatever we want to both sides. And we're just repeating this process until we figure out what one particular x is equal to, what just one of those variables is. All right, let's go ahead and try this problem. This situation now deals with parentheses on one of the sides. If you remember from the order of operations, it says that we need to work in the parentheses first when we plug in a number. So let's say, I don't know, let's say x happened to be the number 7, right? You would add the things in the parentheses first, then you would work out from there. You would multiply, divide, add, subtract. Well, what can I do in this case? I can't go and I combine x and 5 together. X plus 5, that doesn't combine because those aren't like terms. Remember, like terms here, like terms are terms, and I know I just used part of the word in its own definition, but terms are, think of them as numbers or numbers of variables together, the things that are being added or subtracted together. We can think of them like that. So terms, like terms I should say, are terms that have the same variables and they have to have the same exponents. Do x and the number 5 have the same variables? No, they don't, right? Obviously, you can't add x and 5 together. So we're stuck, it would seem. Well, there's a couple things that we could do. Again, we need to try to get x by itself. So what I want to do is go over the distributive property. Let me jump a couple pages back here. We have these properties of equality, the additive and the multiplicative property. Let's go ahead and let's talk about the start over. So since we can't add x and 5 together, it seems that we would be stuck. So what I'd like us to do right now is to try to think about what this left-hand side means. 3 times x plus 5. That's what it means when a number's next to something in the parentheses. It means multiply. 3 times x plus 5. Okay, well, if I'm taking x plus 5 and multiplying it by 3, that means I take x plus 5 and I'm adding it 3 times. Because that's what multiplication is. It's repeated addition. Remember, if I had 3 times 7, that's the same thing as 7 added to itself 3 times. Okay? To get 21. So, x plus 5 times 3 is just x plus 5 plus another x plus 5. And that's equal to 15. Okay. Well, let's try to combine the like terms here. I have an x, another x, and a third x. So I have 3 x's. And then I also have the number 5 3 times. So 5 plus 5 plus 5 is 15. Take a look and see if you can go from where we started and notice a pattern to get to where we just ended up. 3 times x plus 5 equaling 15 is where we started, and we're ending up with 3x plus 15 equals 15. What do you notice about this? What pattern are you seeing here? Well, hopefully you're noticing the pattern of distribution. What we can say here is, sure, you could go ahead and write all of this out. It wasn't too difficult, but what happens if instead of 3, what happened if we had 21 times x plus 5 equals 15? Or instead of 21, what if I had 96? Do you want to have to write all of those x plus 5s out 96 times? No, you don't. You want a shortcut. So hopefully you're seeing that the shortcut we're discovering here is that of distribution. What distribution says is, if you have a number times an expression in parentheses, right? Multiple things in parentheses, you can multiply each of the terms in the parentheses by the outside number. So 3 times x is 3x, and 3 times 5 is 15. That's what distribution means. Instead of multiplying the number to the whole thing, multiply the number to the individual parts that are in the parenthesis. Let's pop back a few pages and let's define that. So I'm going to define this under the properties of equality. I'm going to include distributive property. So let's start by saying A times B plus C. Let's say you took some number and you multiplied it by these two numbers are being added together in the parentheses and you're multiplying it by some number on the outside. This is the same as A times B plus A times C. You can go ahead and actually multiply the individual terms by that number. This is going to be helpful to us when we start simplifying and solving multi-step equations. Let's take a look at some practice problems here. Notice in this first case, 2 times x plus 3 is equal to 10. Well, you could rewrite this with division or with addition, but let's go ahead and let's try this using the distribution technique. 2 times x plus 3, well, I could multiply the entire outside by 2, the whole thing by 2, I should say. But distribution says I can multiply all of the terms inside of the parentheses by the outside one. So we end up with 2x plus 6 is equal to 10. All that I did was I took the outside number 2 and multiplied it to every single thing in the parentheses. So this is a very simple problem to solve. I'm just going to subtract 6 from both sides. 2x is equal to 4. And then let's divide 2 on both sides. So x is equal to 2. Go ahead and take a look at the second problem. Pause the video, give yourself a couple minutes to solve this one. All right, well, hopefully you're repeating the same process. You're recognizing that we can take the number on the outside and multiply it to the x and to the 4. I'll show you, here's where a common mistake students make. They forget to include the negative. Remember, it's this whole number times x, and that whole number times 4. So negative 3 times x is negative 3. Negative 3 and 4 makes negative 12. I carried the sign along with it. That's important. Make sure you do that. I can go ahead and solve this pretty quickly now. I'm going to add 12 to both sides. And that should come out to 25. Then, to get the x to have a 1 coefficient, I'm going to divide both sides by negative 3. And we end up with x is equal to negative 25 over 3. Here we're just using, again, those simple properties of equality to get x by itself. All right, well, hopefully this is starting to come back to you and it's making sense. I want us to really make sure that when we're using these properties, we're recognizing them, recognizing why we're doing certain things in class. If you have any questions, feel free to let me know. My email is klinford, that's KLINFORD, @wccnet.edu. Until next time, take care.